So we moving into section 9.5, and as we already noticed, the series are series, they're always around us, and let's say always, well, in this textbook at least. And we just see this alternating sign series that shown here. It's like a geometric, but the powers are 2, 4, 8. So it's like first power, second, third, fourth. So it's geometric. So the radius of convergence, the coefficient for geometric series is -1/2, which is less than 1, right? And if so, if in absolute value, see now we see why absolute value was utilized. So if it's less than 1, I'm going to write less than 1, then series is convergent. So as series, as R is less than 1, then series is convergent. And also we can find the sum of this series, and because it's geometric, right? And that's what we did already. And looks like 9.5 does not bring us anything for this particular example. But, and that's what they say, radius is -1/2. But what they do is they go deeper. So they say if this alternating series, and if there is another condition, the terms approach to, looks like they have this here. The next term is going to be smaller than the previous term. So we see the terms here, and this is a half, and the next is smaller, it's a quarter. And the next is again smaller, it's 1/8. So the second condition is also stressed here. Then this series is convergent. And of course, we know it is convergent because it's geometric for that particular example, but this is in general. This is in general. So one can say, if we just take -1/n, actually 1/n, that was divergent series. Let me start like that. So to refresh your memories on what we already should remember. If not, it's fine. You don't have to remember anything. You can just write it down, right? So the harmonic series, which is divergent, harmonic. But if you're going to turn it into alternating series, how? Well, I can put -1 to the power of n and multiply by my harmonic series, and I'm gonna start at 1, not at 0, because at 0 we're gonna have 1/0. The first term is gonna be undefined. So this is gonna be like a -1/1, which is -1, and then plus 1/2, and then -1/3, and then plus 1/4. So harmonic series, then they will be convergent. And that one, which is 1 plus 1/2 plus 1/3 plus ... was divergent. And you say, well, Alex, it's not really surprising because the sign alternating series looks like has not that much added. So why is it divergent? Because you keep on adding more and more, and so you keep on increasing your sum. So remember, we called sum as S. And that was actually infinite. But if we start to alternate signs, so one is negative, the other is positive, then again negative. So you're not really increasing, but you could add something, but then you take it away. So you're not really adding that much as in, remember, it was like a borderline series that was divergent. And this is convergent. So it's good to realize that it's convergent because of a special statement that says the limit of nth term is 0. So notice that limit of your nth term, 1 over n, is equal to 0 because 1 over big turns to be small or 0 when n approaches to infinity. Always need to know what happens with n. Well, with series, it's always n goes to infinity, right? So alternating series test is way more relaxed. In fact, remember, we used to have in the very, very beginning of the story about any series a statement that says if this is convergent series, then limit of nth term must be 0. But it didn't work backwards. What does that mean? Well, it means that if you start at a limit here, then it didn't have to be convergent. And the counterexample is exactly our harmonic series, as well as there's tons of other counterexamples. But we see that limit of 1 over n is 0, but it doesn't follow that series is convergent. In fact, it is divergent, right? Well, in alternating series, if series keeps on changing the sign, it works. It works for alternating series. So if you have limit, I'm just copying the same thing again, is equal to 0, then alternating, and that's the key part, series is convergent. So it makes it be a biconditional statement, which is always a good to have. So you have one thing, then right away you conclude the other, which is identical statement. So sign alternating series. So if we have this factor -1 to the power of n is going to be convergent if its n terms approach to 0. In fact, one can say if nth term does not approach to 0, well, then series is divergent, right? In fact, that's what we already utilized, if you remember, that big statement for, so if we have a series with its nth term, let's say 1/2 or whatever, so if every term is not going to 0, but, well, something not 0, let's say 1/2, then it's going to be infinite or divergent, and that's the idea. So it's kind of intuitive that you can come up with this idea. So I say, why is this infinity? Well, take enough terms. So let's say it's bigger than whatever number you can imagine, billion. We'll take 2 billion terms because series are infinite. So if you take 2 billion terms, the sum already going to be a billion. So you take billion first term, so it's more than a billion. You take another big number, trillion. So take 2 trillion terms, and it will exceed trillion. So the sum is not bounded, it's infinite. To show that sum is infinite, we can say it's bigger than whatever number you can imagine, right? Trillion or quadrillion or whatever. Google, right? Just take twice Google many terms, it's going to be already a Google. Right? Let's say, what is Google? 1 and 100 zeros, right? That's how they call Google. They just spell it a little different. There are various big numbers that have names that we don't really work with. They're huge. But anyways, the point of the story that biconditional statement is working for so-called alternating series, so signs need to alternate. And they may start with a positive one, or they may start with a negative one. Like if you started your first term not a 0, but at 1, so the first term will be negative 1/2, so the first one will disappear. So it might start with a plus, it might start with a minus, as long as the signs will alternate. And that's what the section 9.5 is talking about, all series that have signs that keep on changing. So here, for example, they put not -1 to the power of n, but n plus 1. One can say, so what's the difference? Well, the difference is that your first term is now going to be with a plus sign. So it's going to start not with negative, but with a positive 1. And that makes no difference in terms of sign alternating series. So there are various things, as long as there is minus involved and there's some power of n, then you have this kind of story. So what's interesting is so-called absolute conversion. So technically, what we were working with so far was absolute conversions, because we did not really work much with the sign alternating series. All series we worked with were with positive terms, or some people here can say, if I take absolute values of numbers in order to make sure that everything is positive. And one can say, looks like indeed, if everything was positive, it's kind of stronger for conversions purposes compared to some of these terms with minus signs. So your sum is going to be definitely lower, because it's not always being increased. Sometimes it's going down to the right, and then you increase it a little bit, but then again going down. So that's interesting to realize, and we now kind of make the story a little bit finer, so not as crude as was before. So the statement we just made, it says, if series is convergent, then the series without absolute value is also convergent. And that's actually what we were heading towards by comparing these examples with everything positive and some of them with negative, so some terms alternate. But anyways, that's what we used to do as we worked with convergence and absolute values. And this is pretty often appears when you deal with trig terms, like sine or cosine involved, or some other functions, trigonometric nature, because they automatically give you pluses or minuses, right? So let me say, what's the reason for that? Well, look at the graph, that'd be the reason. If you look at the graph of function, cosine, for example, right? That's a cosine of x. That is, of course, repeated, hopefully infinitely many times, to the left and to the right. And it varies from minus to plus 1. So if you are going to have it, the trig function as a part of your series, then notice the values will be y coordinates. So this graph will change its sign from positives if you down below the x-axis to negative. And eventually, of course, they will turn into alternating sign sequence. And that's why people say if I take the absolute values of this type of series, then if that series with absolute values converges, well, then the original series is also going to be convergent. And why is that? Well, because we see that this is analogous to another conversion, so-called p-series. Remember, if you have a sum of 1 over n, that is divergent, but if you put a power more than 1, so if p is more than 1, it's 2, in this particular case, it's n squared. As long as it is more than 1, then it's going to be convergent. So we saw this before. Again, if you forgot, well, just check out our previous lecture recording because it's there and it's good to, well, be at least able to find where this is. So that's another big convergence statement. So whenever p is power of your denominator is more than 1, so it is convergent. So they already think that you know it. See, they don't even write why, so they say it's convergent, that's it. But we need to know why, right? And definitely sign in absolute value is less than 1 or maybe equal because it's either plus or minus 1 or anything in between. So it is definitely correct statement. So if dominating series, that so-called comparison test, dominating series sum of 1 over n squared is convergent, then the smaller term series is also going to be convergent. So they didn't really write what this test says, but what it says is as smaller is larger series convergent than smaller term series. Smaller is what was shown with inequalities because sign is less than 1 in absolute value is also convergent. So lots of little steps are missing, lots of gaps that they expect you to be able to fill. That's the idea. So anyways, our story was if absolute value series is convergent, then series without absolute values is also convergent because it's going to alternate its signs. I'm going to say, well, it may not always alternate, may have a couple of terms with positive signs, but then a couple of terms with negative signs, or even 3 terms. Yes, but we still say it's sign alternating series. So it doesn't really have to be always plus minus plus minus. It may be 2 pluses, 3 minuses, 2 pluses, 3 minuses, and that way we could still use the same exact facts. So that's important to realize that one does not to be very rigid in terms of these little statements and definitions. You should be able to vary them. But again, the more we talk about it, the more comfortable I hope you will be doing that. So absolute conversions in absolute values, and that's what we discussed here. And so-called conditional conversions, it's the case when absolute values diverges. When absolute values diverges, which is here, for example, again, my favorite harmonic series. Well, I use it because we are familiar with it. Of course, there are tons of examples, but the one that I'm using here is the favorite harmonic series because if you have it all positive, it's divergent, right? But if you start to have it divergent, but if you have sign alternating down below, then it is conversion. So if you have absolute values divergent and without, so with absolute values, but without absolute values is here is conversion. So looks like it's conditionally conversion. Conditionally convergent example. That's worth to think about it because I know those may seem to be straightforward as usual when I discuss it, but then you start to think about it and you need to really give it a little time and then it will click and say, oh yeah, now I see what this means. So this is interesting. So I guess we can try to take a look at some of the examples. And I can say we keep going through examples here all the time. Yeah, I can try some from the end of the section because the section is actually pretty short. So I can try one example here, like the one, for instance, with so geometric series, not interesting. Maybe next page is good. Yeah. So on the next page, so let me try exercise number 15, for instance. What can you say about its convergent or divergence? Well, all I care about is a limit of n's term. Remember, it must approach to zero. If it's approaching to zero, then we have convergent series in terms of absolute values. So what about this one? Well, we need to find the limit of that nth term. And please notice when I take the limit -1, I don't really care for because it just keeps on alternating. So I just take the limit of absolute values. So without that -1, so this will be just 5n minus 1 divided by 4n plus 1. And we already know when n approaches to infinity, we always use the same thing here, like L'Hopital's rule. So you can take derivative of your numerator and derivative of your denominator. So when you take derivative of numerator, it will be 5, right? Because first power of x or n will become 1. And for denominator is 4. So it is not 0. So not 0 means series is divergent. Absolutely. In fact, conditional convergence is the same. So we must have the nth term limit equal to 0, not to 5/4 or some other non-zero number, because otherwise series is divergent. So when you found the limit of nth term not equal to 0, that's it. Divergent series. Very straightforward. Right? So with these things, I guess the exercises become pretty straightforward. So let me do exercise 20. Analogous format. Look at this. Without the -1, looks like limit will be zero, right? Analogous to 1 over n, where we can just care about power of the top is 1, power of the bottom is 2, so I can cancel by one of these n's, so it'll be 1 over n, which approaches to 0, right? So limit of nth term is 0, then series is convergent. And since the series is sign alternating, then it's convergent absolutely. Absolute convergence is pretty strong kind of convergence. And that's all. So we determine that series is convergent. Or divergent. So first was divergent, second is convergent. Well, there is an amazing thing I think I promised to tell you last time about this series that sign alternating. So I think I need to use eraser a little bit to erase this mess. So we can look at example 7. I'm not gonna go through all of the little steps. If someone is really interested, we can definitely do that. It's a little bit time consuming because it refers us to example 59 in section 910, which is actually a little later. So a little later, we can definitely take a look at all that. But the point of story is if you have series that converge absolutely, but do not converge actually, that converge but do not converge absolutely. So again, our example of harmonic series. So here we also have harmonic series, right? 1 over n. It turns out it can converge to any point. Let's see, what do you mean? For example, ln of 2. So if you have a sign alternating series, it may converge to ln of 2, or it may converge to half of ln of 2. Let's see, so what? It converges to ln of 2 or to a half of it? To both. And that's the amazing thing. How is it possible that there is conversion to here as well as to here? It's infinite series. And when we get to infinite type of a structure, it behaves in such a way that we cannot comprehend it. And that's what this statement is talking about. So if series is conditionally convergent, like the one we have here, then turns out if you try to rearrange the terms, instead of conversion to ln of 2, you can factor out a half, and it will converge to a half of it. Or you could factor out any number whatsoever, so you can say that it's actually converges to any real number, which is pretty amazing, really amazing fact. So conditional conversion series converge to any real number. See, conditional convergence is really something that one cannot really comprehend then, because how can this be logically possible to convert to any real number? It makes no sense. Well, in absolute values, it's not convergent, it's divergent. But conditional convergence is something very artificial. So even though we have word convergence, but it is not what we think it is. It's conditional convergence. It can be algebraically made to be convergent to any real number whatsoever. That's pretty odd, right? But that's what it is. So it's actually been proven here and back in the years. So when you say there is something fishy about this, well, yes, well, then it's good to realize whenever we deal with infinite sums, unusual things possible. Amazing. So I guess example 7 is something definitely voluntarily, but anyways, I'll move on to something more straightforward, to another nice test. I think the only test we're gonna look at today is ratio test from the next section that seem to be in a way similar to what we saw already before. So let me clean the mess. Stop to share. Stop and share it again. So it turns out that interesting test that we probably should have learned a while ago is finally here. And the test says it will converge absolutely, which is the strong, good convergence, if next term divided by the previous term gives us fraction less than 1. So how does this work? Well, absolute convergence, my favorite harmonic series. And we already saw it is absolutely convergent. So if I take absolute values, then without -1, it's actually not convergence, it's absolute divergence. So maybe I'll take squared to make it be conversion. So that's convergence series in absolute values. So it'd be absolute convergence. Why is it convergent in absolute values? Well, because it's P series and the power of n is more than 1. I just had it here somewhere and erased it. So if I look at the quotient of n plus first term divided by the nth term, how can I produce that? Well, first of all, notice that's absolute value, so the negative sign is not relevant. So I just divide n plus first term, which is 1 over n plus 1 squared over 1 over n squared. So I need to find that this limit is less than 1. Well, let's find out. Let's do a little bit of algebra. So this is going to be n squared divided by n squared plus, no, it's square n plus 1. So it's n squared plus 2n and plus 1, right? And again, by L'Hopital's rule, if I take the limit of that, it will be just a quotient of leading coefficients, right? Leading coefficients. Here is 1 and here is also 1, so it's 1. I see. So what, Alex? Did you produce your limit less than 1? No, it is 1. It is not less than 1, but it converges when limit is less than 1. And it diverges when limit is greater than 1. And our limit is 1. So it's not covered by that. I say, so did you take a bad example? Kind of, but I was able to show you that it's not always working, because if your limit is 1, you cannot use this test. But I already know that this is convergent, right? In absolute values, 1 over n squared, because power of n is more than 1. So I didn't really need to test it, but the idea that you cannot apply this particular test. So one can say, okay, Alex, when can you apply it? Well, when I was not able to do it before, turns out, with factorials, with powers, and that's type of examples we see here. So I can, instead of repeating the same thing, just get you one from the end of the section with factorials. I was kind of avoiding using the exercises with factorials because they are awesomely done by this particular ratio test. So if I try one, let's say here, for example, 15, we would not be able to do it before unless we would use the series comparison test that is always not much fun. So if I try to look at n factorial over 3 to the power of n and see if it's convergent, when say, Alex, is that absolute convergence? Well, these terms are positives anyways, so if you take its absolute values, it'd be the same thing. So technically, it is going under the test, even though there are no minuses, but you could treat it as if it was positive, right, in absolute values. So I put, again, instead of n plus 1, and that will be for my fraction 3 to the power of n plus 1 on the top, and on the bottom, it will be n factorial and then 3 to the power of n. So now I want to see that this limit is less than 1. So I need to find the limit when n approaches to infinity. And notice that algebra will cancel lots of little things here, right? So I could write n factorial, n plus 1 factorial as n factorial times n plus 1, right? What is n factorial? It's n minus 1, n minus 2, all the way to 1. So n plus 1 factorial starts with n plus 1, then n minus 1, so all the way to 1. But I don't need to continue because all I have is n factorial that will cancel with n factorial from the bottom. So I take this denominator and flip it. So I'll put 3 to the power of n on the top and n factorial on the bottom, flip it. And now I will enjoy some of the canceling. That's the part I really love. I love to cancel. So we have limit of 3n plus 1. Oh, it's just going to be 3 on the bottom and n plus 1 on the top, right? And this approaches to what? This approaches to infinity. Is this convergent or divergent? Well, it is definitely greater than 1, so the series is divergent. If you remember, a while ago I said that n factorial is the fastest increasing function. It beats the exponent. It's dominating. So no wonder the limit is infinite. If n factorial was in denominator, then it'd be 0. So greater than 1, series is indeed divergent. And probably it's a good moment to stop, and we'll do more of this next time. In fact, this section has another test, which is not very relevant, and just a very few exercises can use it. But so the key test is so-called nth term test, or ratio of n plus first and nth term. So anyways, to be continued. So I will stop at this stage. I guess it's getting too much anyways, right? So